Hey yo, welcome to Astronaut. Today we're talking about gravitational lensing, when the gravitational fields of an object forces light to bend around it.
I feel like an astronaut in what you know about rolling down in the deep.
What is gravitational lensing? Although the term may sound obscure, gravitational lensing is exactly what it sounds like. Gravitational lensing is the lensing, that is, the bending or distorting of light, of an object due to gravity. Gravitational lensing is based in general relativity, which states that gravity warps spacetime. This implies that the path of light will bend around an object with a gravitational field. For lensing to occur, three things are needed. 1. A distant object, for example, an ant. 2. A lens, like a magnifying glass. And, of course, 3. An observer, someone or something to process the incoming light. As light from the distant source hits the lens, the light rays will converge towards a focal point and then refract at an angle. Since we process light as though it travels in a straight line, we will view the object as larger than it actually is. A similar process occurs on a galactic scale. In this case, the foreground object, generating a galactic field, for example, a galaxy or cluster of galaxies, acts as a lens. As we observe an object in the distance, like a star, the foreground object distorts the light from the background source, causing it to bend in the direction of our telescope. With gravitational lensing, we can gather information about objects that are far away that we would not otherwise be able to see. The James Webb Space Telescope, for example, is being used to observe early star formation in distant galaxies with the assistance of gravitational lensing, which magnifies the galaxies. Additionally, gravitational lensing allows us to map out things like dark matter, which can act as a lens. An object that is distorted without the presence of visible matter suggests the presence of dark matter. We can calculate how the light will be redirected. If all three objects are aligned, the light from the source will be redirected by an amount b, which we call the impact parameter. The observer will see an image of the source at an angle theta. The angle of deflection is the angle at which this image forms with respect to the source's deflection. We can also label the distances between the observer, lens, and the source. I'll use subscripts to denote which distance is being referred to. Einstein derived that the angle of deflection is equal to 4gm over c squared b. Tan theta equals b over the distance between the observer and the lens. By the small angle approximation, tan theta equals theta. We can rewrite this as b is equal to theta times the distance. We also know that the angle of deflection is equal to theta times the distance between the observer and the source, divided by the distance between the lens and the source. Combining these equations, we get that theta squared equals 4gm over c squared times the distance between the lens and the source over the other two distances. Finally, we can take the square root of both sides. If the source is a point, like a quasar, a perfect circle of light will form, which we call an Einstein Ring. The radius of this circle is called the Einstein radius. In this example, photographed by the Wide Field Camera 3 of the Hubble Space Telescope, a distant blue galaxy bends around a luminous red galaxy in the foreground. Well, that's all for today. Thanks for watching, and as always, ponder, wonder, and go right in the stars.
In slow motion, yeah, I feel like an astronaut.